All right, let's get started. So welcome to another ACM seminar. So we are very happy to have Dr. Lee from KIAS, Korea Institute for Advanced Study, and Jae Yong got his PhD from Postech under guidance of the Professor Hongju, and he's now at KIAS Fellow. And we were going to talk about today on two approaches using deep learning to solve partial differential equations. So let's welcome Dr. Lee.
Thank you for introduction and invitation. I plan to have a presentation in Korean, but they're foreigner, so I'll do in English in this presentation. And today's my presentation title is Two Approaches Using Deep Learning to Solve Partial Differential Equation. And there are two mainstreams to solve partial differential equation using deep learning called PDE solver and operator learning. So today I'll introduce these two approaches about this title. Yes, so let's start. So first, PDE solver is about to solve one PDE using deep learning. So the famous model is called physics-informed neural network, called PIN. And I'll introduce my interests about that PDE solver part. And then I'll introduce the operator learning. And one of famous model in operator learning is deep operator network. So I'll introduce what is deep operator network. And then I'll introduce my interests on operator learning. So today's presentation will cover these two approaches today. So as maybe you already know about that, but if there are no background on PDE, so I'll introduce this PDE, partial differential equation. In mathematics, differential equation is an equation that relates one or more functions and their derivatives. So function is generally represented like physical quantities, and the derivatives represent their rates of change. And so the equation defines a relationship between these above two. So for example, I have an example for called heat equation. If we have a solution UTX, which depends on T and X, so UTX denote the temperature at point X at time T. Also, we have a domain from 0 to L. So if we want to express the change of temperature depends on T and at each position X, then we have a governing equation, heat equation like this one. Also, we have two more conditions. First one is initial conditions to represent what the initial function which we have at initial state, and we also have a boundary condition because in this case the domain is bounded. Then each side of domain has a boundary condition. So if we have these three conditions, then we can if we can solve this system of PDE, then we can find the temperature at each point X and at every time T. So it's a purpose of PDE. So also today I'll introduce about deep neural network and deep learning to solve PDE. So I'll introduce deep neural network briefly. Deep neural network, as you know, deep neural network takes an input from X1 to Xn, and they make an output in the final layer. And each layer, they want to approximate the complicated function using this like complex structure. And then each neuron has the right side explains of each neuron. Each neuron has the activation function and also bias and weight parameters. So if we want to approximate some function f using this deep neural network, then we can and we want to find the parameter w, which is called weight, and the bias which is this maybe there are no bias, but weight or bias is we want to find these two parameters to find this neural network. So the learning deep learning means that we find the optimal weight and bias, which that makes this neural network to approximate the target function. So as you already heard about that, deep neural networks can approximate many complicated functions. So this deep neural network and its more advanced structures are used to approximate something like image segmentation or image to image regression or other things. So today I'll use this deep neural network structure to approximate PDE. This is the first approach using deep learning to PDEs. I call this approach is PDE solver. The PDE solver means that, for example, I have an example. If we have a PDE like this one, and also I have an initial condition and boundary condition, then in this case, in this approach, we want to find UTX, which depends on T and X. So we can naturally think about this deep neural network, which takes an input T and X, and the output will be a UTX, which depends on T and X. So the purpose of this approach is to find the optimal weight and bias that the output U neural network TX satisfies these three conditions. So later, like deep leach method or physics informed neural network is an algorithm how to find the weight and bias which satisfies this output satisfies these three conditions. So in this case, if we want to use this approach, we have to know about this instance of PDE, equation, initial condition, and boundary condition. And then we can solve this one using deep neural network, which parameterize a solution of this PDE system. So the main characteristic of this approach is to solve one instance of PDE at a time. So today's presentation, I'll explain about this physics informed neural network rather than this deep leach method. So on the other hand, there are another approach called operator learning. As you heard about operator, it means the mapping from function to function. Then in this case, for example, if we have a PDE initial condition and boundary condition, and then we want to find not only U, but also we want to find a map from GX to UX, which GX is in, for example, in the condition.
PDEs to the corresponding solution. Family of PDEs from there. Learning a family of PDEs from there.
Can you say that again?
Were there any questions from the audience? No?
No.
Okay, you can carry on.
Okay. So if you have a question, and you can interrupt me anytime, and you can ask a question in Korean. It's also possible. So in this case, the solution of PDE called U will be different corresponding to this initial condition GX. So if we have a different GX, then the solution U will be changed, depend on GX. So in this approach, we want to find the operator from GX to U TX. So in this case, the input of the neural network is GX, and the output is UTX, which depends on GX. So this operator learning is to learn a mapping from the parameters such as external force or initial condition or boundary conditions of the PDE to the corresponding solution. So in this approach, we call this operator learning learns a family of PDEs from data. So there are two famous models. First is DeepONet, which is deep operator network. And the second, the famous one, is free neural operator FNO. But today's presentation, I'll briefly explain about DeepONet rather than FNO. Okay, so my interest is about these two approaches is follows. First, my interest is to use this PDE solver approach to solve complex kinetic equation. So later I'll introduce what is the kinetic equation and how to use this algorithm to solve kinetic equation. And the second one, my interest is about this operator learning. First one is to improve and to generalize the DeepONet. So also I want to use this operator learning to solve PDE constraint control problem. And finally, I'll introduce briefly about this combining algorithm using PIN with operator learning to solve the complex PDEs. So today I'll explain this my researches. So yes, so first I'll introduce the PDE solver more explicitly. There are many traditional numerical methods. In this picture, I have explained about finite difference method. In this case, if we have this PDE called Poisson equation, and then we have to discretize the grid, and then each grid has a value of this u at each grid, and then we have to discretize this differentiation term like this one, and then if we have a value in each nodes, each grid, and then we can calculate this all u values at each point using these relations. So it's FDM, and there are also many other numerical methods, such as finite elements method, which is, for example, we discretize the domain as a triangularization, and we have a local basis in each domain, and then we want to find the coefficient which is related to this local basis. So there are also many other numerical methods. Here I want to introduce another way to solve PDE using deep learning is PDE solver. In 1997, there also exists about PDE solver based on deep neural network. For example, in this paper, they have an example like this one. If they have a Poisson equation, and this is the boundary conditions for this equation, and then they can think this trial solution to make this to make the solution in this equation, and they make a trial solution as follows. They make phi equal to a and x 1 minus x y 1 minus y and neural network. If they make this trial solution, then as you know, the domain is 0 to 1 for each x and y. Then if we take input, take the value x at 0 or 1 for y 0 and 1, then this term is erased. So if they can find this A satisfying these boundary conditions for F0, F1, G0, and G1, then they can make exact they can enforce the boundary condition to satisfy this trial solution. And then they want to find that neural network term to satisfy this equation. So in this they use this idea to enforce these boundary conditions. and they have to find the neural network for focus on this first equation. And then they want to make a neural network parameterization, which takes an input xy, and the output is neural network xy. And then they can find this neural network parameter p. As I said, this is the network parameter weight or biases in each node. So they can make, they can find this p by minimizing this error, which is the residual error of this equation. So here, so we have we can have a question: how to calculate the derivative of this output with respect to any of its inputs, x or y? Because in FDM, it's the core idea, because we can discretize these grid points and we can calculate this derivative term as follows. And in this case, how can we calculate this one? So they said that if we have this one direct neural network parameterization, then we can calculate the derivative using chain rule, because if we want to derivative this one with respect to this one, and then we can calculate this derivative, this weight or parameters, and also we can calculate this output with respect to this output. Also, we can calculate derivative term, this output with respect to this xy. And they just use chain rule to calculate this derivative term. So the PD solver based on neural network has appeared in 1997. And then recently, the famous model is coming, called physics informed neural network, called PIN, in 2019. They also use this neural network parameterization, but they said in their paper, they said that they just visit them using modern computational tools such as automatic differentiation or backpropagation algorithm. So these algorithms can be used using PyTorch or TensorFlow in recent days. So they just use this GPU like these resources to calculate these derivative terms very fastly. So it's the big difference between this history and this PIN. So they use that GPU resources and computational tools to solve these PDEs. And then they also take on input TX using deep neural network, and the output is U. And also they can calculate these derivative terms using chain rules. Also, they can make a residual value of this PD. And then they just minimize this one. And then they repeated this called approx to learn of optimal parameters, weight, and bias. And then they can find the optimal weight bias to which is the minimize, which is the direction to minimize this residual. So this solution U will satisfy the equation because the residual is minimized. So this is the core idea of this PIN algorithm. I have an example for this one. If we have a Burgers equation like this one, equation initial condition with boundary condition, and the domain is -1 to 1 from time 0 to 1. And then they can make a loss function like this one. The first term is just the residual term of this equation at each grid Ti and Xi, which is sampled in this domain. Also, the second term is about initial condition. So for the initial condition, we use the grid Tj and Xj on this domain. Because for initial condition, we just take a sample at time t equal to 0. So they have a sample grid samples, and they can calculate this one for the initial condition. Also, the last term is about boundary condition. The grid points tk and xk is in this one because we have to sample only in boundary. And then using these grids, we can calculate the last term. And we have these loss functions, which consists of these three terms. Then they just want to minimize these terms, these three terms. So they repeat this learning algorithm. Then they can find the optimal weight and bias to satisfy these three conditions. So this is the core idea of this pin algorithm. Using this algorithm, they can find this optimal weight and bias to satisfy these three conditions. So it shows that the prediction solution, neural network solution U, is almost same as the exact solution. So this approach has many benefits and drawbacks. There are many ways to explain these benefits and drawbacks, but in this table, they show some very important benefits for this approach. For example, they can use this algorithm for arbitrary domain, because as you see this one, if we can sample just in that domain, then we can learn this algorithm. So it's different to this FDM, because in FDM we have to discretize domains. So in complex geometry it can be difficult, but in the case this physics informed neural network can have a big advantage because they just sample points in that domain and they can train these loss functions. So it's one of the benefits in this approach, but also there are many drawbacks. The most important drawback is convergence, because if we train this neural network using this algorithm, then we don't know about this convergence of this algorithm, because this deep neural network is based on gradient descent and its variance. So the convergence of this algorithm will be very not exact and very big issues in this approach. So there are many benefits and drawbacks. So we can think this approach is another way to solve PDE parallel to other numerical methods. So first, my interest is about this PDE solver is using pin to solve the kinetic equation, such as focal Planck equation. In kinetic equation, they have three variables, t, x, and v. And ftx, v represent the probability density distribution of particles at time t at position x, which has a velocity v. Then, if we have this equation, the right term expresses the collision in this distribution with this initial condition, and also we have a boundary conditions. For example, if we have the specular reflection boundary conditions, means that when the particle comes to this boundary, then it reflects in the boundary at the same angle. And also there are many physical boundary conditions, such as observing boundary conditions, inflow boundary conditions, and so on. So in this case, I want to use this pin algorithm to solve focal Planck equation for various types of physical boundary conditions. And also, we already know about this equation. In this equation, we have a mass conservation in this equation. So if the particles reflects in each boundaries, then the all number of particles will have no changes. So we can take that terms as loss functions to approximate this PDE solver. Also, I want to provide the theoretical support for the pointwise convergence of this neural network solution to the priori analytic solutions. So here is one research about my research. If we have this boundary -1 to 1, and if we set this like cake shape initial conditions, in this picture we have the at -1 is the here, and 1 is the here, and this graph shows for each some several positions. And if we have the initial distributions as follows, and then we already know if we have a specular boundary condition in each boundary, then the particle, all positions have a same shape called Maxwellian, which is also same as Gaussian in all positions. So as time goes infinity, then all positions will go this Maxwellian shape. So it shows that the pin for kinetication works well, which is the consistent with to this theoretical evidence. Also, I want to give a theoretical evidence about the convergence of solution to the real analytic solution. Here, I just briefly introduce about this theorem. In 1996, there are also a theorem about this universal approximation theorem on derivative terms. And this shows that if we want to approximate the target function f using neural network, then we can find these weight and biases which is very similar to this function. And this theorem says we can find also the target derivative of target function is same as derivative of this neural network with respect to input. So this is the universal approximation theorem on derivatives. And using this theorem, I just want to show the convergence in these two steps. First, I want to explain about the loss functions. So in the first approach, I want to show that there exists a parameters of neural network called weight and bias that reduce the loss function as we want. Because the loss function is just residual of this equation and boundary condition and initial conditions. So I want to first I want to show the loss function can be reduced as we want. Also, the second way, I want to show that the neural network solution converges to an analytic solution when the loss function is reduced. So when I show this theorem, I used this universal approximation theorem on derivatives.
Can I ask a quick question?
Yes.
So in your loss, do you use the discrete height loss, or are you assuming the continuum loss that you find to be the complete?
When I show these theorems, I just use the continuous loss, which is L2 norm for the residue.
Ask one more question. So in your simulation research, I wonder how you enforce your neural network to be density function, because you have to ensure that the integration of all has to be one, which require, it seems that without doing any trick, it requires you to somehow way to ensure that your integration of our entire space should be one uniformly in T.
Right. So
can you a little bit comment on that?
So as I said here, I already as you said, we already know the conservation of the total mass. So I just put the total mass at any time as loss functions to satisfy, to enforce the volume of this distribution is 1.
I see.
And also the one trick is one more important thing in this case is the distribution function has always the positive.
Right.
So I used the last layer with activation function called soft plus. If we can use that activation function, then the output will be always positive. So it is one of trick in this idea.
Do you have 2D examples on that?
No. In this paper, I just do 1D.
Do you think is it hard to extend it to 2D or 3D cases?
Maybe it will be easy because we can just use this algorithm for multi-domain. But when we calculate these derivative terms to make a residual loss of this equation, for example, 3D, then this equation has 7-dimensional because t and 3-dimensional for x and 3-dimensional for v. Then it will be very it will have a very large computational costs, need this large computational cost, but it can be used this algorithm to solve that case.
Thank you.
All right. So this is one of my presentation for first part. And the second part, I'll introduce about the operator learning. As I said, the operator learning is a mapping between function to function. So this operator learning is a mapping from infinite dimensional function space to infinite dimensional function space. So there are many studies to learn operator, not only in PDE case but also other just operator. And one of the common core problems is mapping from the parameters of PDE to the corresponding solutions. So it is the one of the example in operator learning. For example, in dam brick scenario, when we have this initial height at each position, then as time goes 0.5 or 1, then this dam brick is like changes into this like different shapes. So in this case, if we use this operator learning, then we want to find from this initial condition to any time height for each position x1, x2. So it is the one of example to use operator learning. So traditional numerical method also can be used to solve this PDEs and this operator. But in the numerical method, when we use traditional numerical method, we have to solve this PDE for different initial conditions. So when we have an initial condition G1 in here, then we can have to solve we have to use numerical method to solve U1. And if we have a different initial condition G2, then we also have to use again this numerical method to solve this PDE to find U2 and so on. But if we use neural network, and we also have we assume that we also have a data set GI UI, then we can train this neural network from GI to UI. Then if we use this data set to learn this neural network, and then if we have a new G new for these initial conditions, and if we want to find this U corresponding to this G, then we can just inference this, we can just use this neural network to find this U, which is correspond to this G, initial condition G. So there are two famous models called deep operator network and free neural operator and other neural operator things. But today I'll just explain about this deep operator network. So before that, we can think the natural approach to learn this operator in computer science, there are many tasks using this like convolution neural network, which want to target this image to image regression. For example, image segmentation or image noise reduction or image coloring. So this network takes an input as an image, and the output is also image. So in a natural idea, we can think this function as an image. So if we use this network, image to image regression, then for example, if we have a Poisson equation, then if we want to find this M mapping from M to U in 2D case, then we can think M x1, x2 as on 2D images. Because for each position x1 and x2, we have the value of this M. Then we can think these values as an image M x1, x2. And the output U x1, x2 also can be considered as image. The value of this U x1, x2 at each position x1, x2 has a value, and we can think that like that image for U x1, x2. Then we can just learn this M, the mapping from M to U, and we can use this model to predict for a new M, new source term M, to find the new U. But this natural idea has a limitation. If we can use this model only when input function values are known in a uniform grid, because if we want to use this network, we have to uniform values for this input function M. Also, there are another limitation that we can only use this neural network when all input function values are known in all grids. Because if we want to take this function as an input, then we have to know each values on each grid. So this deep ONet can be overcome this limitation, which is appeared in 2021. In this paper, they have a notation like this. They want to learn an operator G from UX to GUI. So this is the input function, and G is operator, so GU is a function which has a variable Y. And then they just assume that they have a training data as follows. If we have this input function U at each fixed sensors X1 to XM, and this one like this, and also they assume that they have a random location Y, which they want to find this GU at position Y, then they just propose this model called deep ONet. They just use two neural networks to approximate this operator. So these two purple box. First one is called BranchNet, which takes an input function UX, this one. And the second network takes on Y, which is a variable in the output function space. Then each network makes length P values, and then they just product these two P values to find this output target function GUI. So in this case, they just discretize this U at some fixed sensors X1 to XM, and the length M vectors is an input in this branch network, and the output is the length P values. Also, trunknet has a P values, and they just product to make that one. So naturally, we have a question why they use this network structure to approximate this operator. They said that they just use deep neural network version of this theorem, which is in 1995 from Chen and Chen. Chen and Chen proposed the universal approximation theorem for operator as follows. and they just use this one and this one in this theorem by using neural network to approximate to make a deeper network instead of these terms and these terms. And so therefore I would like to say that this model is based on universal approximation theorem, and it actually performs well in many various operator learning problems. So in this for my interest, I want to find and I want to analyze this model more explicitly. As you can see this model is just inner product of these two p values. We can think this output of these each neural networks. And first, we can think this output function has a variable y. So the y is just input in this trunknet. So trunknet makes the p values, which is the basis function for the output target function space. So trunknet makes the p basis for the target function, and the branchnet makes the output, which is the coefficient of each basis. And in this perspective, we can think this DBONet has a linear approximation using this p basis with p coefficients to approximate this target function. But using this perspective, we have a limitation of this DBONet, because this is just linear approximation to approximate target function. So if we have a target function, when the target function is discontinuous or sharp, then this linear approximation will need many parameters for each networks. So here I want to make a general version of this model. So we can think this DBONet in this perspective. We want to find GUI. We want to approximate GUI. So GUI takes an input y, and the output is G zeta UI. And the core idea of this model is how to put the information of input function u in this model, in this network. Then DBONet can be thought as this as follows. This target network is this part, and then they just want to give information of u in the last part of this network to inner product these two p values. So in the perspective, they just use branchnet to give information of u in the last layer in target network. So here, the natural idea of the generalized one, to generalize this model, we can give information of u for all layers, not only the last layers. So I propose a called hyper DBONet, which gives the information of u at all layers in target network. Then this model can reduce the parameters when the target function is complicated, discontinuous, and complicated. So this is one of my interests. So here is one quick example. If we want to find an operator from ux to derivative of u, then the DBONet and other variants have a limitation to approximate this complicated target function. But using our model, we can approximate this complicated target function very exactly. So
Can I have a quick question? Have you tried the so-called causality DBONet, so that what they are doing is they introduce the encoder part of the inputs, so that they make the u information to be go into the trunk network part as well.
Ah, really? I
So
see.
that sort of like connects your intuition of the
Ah.
putting information in an encoder way, but extending more input space. So that I wonder, have you also compared your HyperNet with their method?
Oh, I didn't know about that
Okay.
method, but
I will point you out that paper.
yes. And there are many various models. They called shift devoted or flex devoted or nomad. They use the another network to give this information in this input
I see.
layer, and they also have a large parameters to approximate target function. But maybe it is one of the other ways to give this information in this network.
Can you a little bit elaborate why the way you impose might perform better than others? Because it seems that the general idea is trying to embed the input function information into the trunk network in a certain way. And everyone seems doing the same thing in that principle. But can you a little bit comment on that? Why the way you propose might perform better than others?
Because I think that we showed in our paper that if we use this hypernet to give this all information of these target network parameters, then this hypernetwork can be a like information share for each U for each layers. So the hypernet makes the similar information for each layers, which depends on this U. But in this Dbonet case, they just give a U branch net to give this information, and then they have to learn parameters in this branch net also in this one. But in our case, this network parameters is just out of this network. The learnable parameters is only in this hypernetwork. So maybe it is the like that idea.
Okay, thank you.
Okay. So here is the another. Oh yes.
Yes, the next one. To say that here, as you can see, the hyperactive OLED is more efficient than the other methods. But I don't understand how these methods show efficiency.
Efficiency.
Yes.
So I'll more explicitly explain about this figure. If we have this example from UX to derivative of U, then the input function is this red line, and the output function is this red dotted line. In this case, so in this two example, if we take the purpose of this task is using this input function red line to make a prediction this dotted line. Then take a input this one. Other models, Dbonet and other variance models, couldn't have a limitation to approximate this red dotted line using the limited resources. However, our model can approximate this target function red dotted line very well in the third graph shows that. Okay, thank you. Okay.
It is efficient, and could you compare the number of parameters?
Yeah. Yes. We in this case we just use the same number of parameters to approximate this task. So the small parameters is used for Dbonet and other variants, also for other model, our model. And in this case, we just use the same number of parameters to approximate this one. And also in our paper, we proved that hypernet, like this structure, has a smaller parameter, needs a smaller parameter than other variants like Dvonet or other variants.
How much smaller?
It is hard to say, but yes, it is hard to say, but I just should show about that. Yes.
You just showed the graph. So can you say actually how large is the error? The number?
Yes. In our paper, we also have a table, which shows the more exact relative error to show our effectiveness. But in here, I just put the graph. But there are also we just can calculate the relative error for each models to approximate this task. And our model has a smaller relative error than other models. But in this presentation, I just put the graph to show the more effective. Is there any question? Yes.
Is there any example for high order derivative?
Yes. Maybe it can be used that case, but I didn't see that one because here I just said this derivative operator, but before our works, many other papers just want to take a task, just the integration operator. Because when we want to approximate the integration operator, the output will be smoother than the input function, then it will be easy. So other models always focus on that task. But in our case, we want to target the complicated target function. So we just we just take a task derivative operator. But as you said, we can extension this model for twice differentiation or something, but I didn't see that one in other papers, also in our paper. But maybe it will be more hard to approximate because this complicated target function will be appeared in that case, which we have a higher derivatives.
Do you use supervised learning or unsupervised learning?
In this case, we just use supervised learning.
And how many data?
In this case, we just use we use the same number of data in other papers, about 10,000 train set, and we just take tests in 200 test set in this case.
So in the case, okay. In the case that you make 10,000 data, then what is the class of data? Is it just a polynomial or?
It is very good question because for the operator learning papers or works, they just used for input function as like Gaussian random field or just the random polynomial like that, but they don't know why they use that one for an input function to make a data. But in this case, we just use this Chebyshev polynomial as the other papers, similar to other papers, but maybe it is the one of important research direction to give input function space to this model or other models.
Actually, I know the answer. Actually, I asked Google about it. Why you always generate the functions from the Gaussian random field, and instead you don't know anything else rather than throwing function samples from the certain space. And one of the representative way of doing it is the Gaussian random field, because that's the way we know how to draw sample random from the distribution. So that's why their default is the GRF.
Yeah, I know that, but in Gaussian random field, then we have some basis actually, and we just take the random combination of that basis function.
Right.
So the usually the basis comes from some eigenfunctions of differential operator.
Right.
Okay, so in a sense, very good.
Yeah, finite dimensional.
Finite dimensional and also very smooth.
Exactly.
Good,
And bounded.
bounded. So
It's very important direction in this research area. Is there any questions? And there are a few slides. And next one, I want to explain briefly about the application of operator learning approach to solve PD constraint control problem. In this case, we just assume that this equation, Poisson equation, with Dirichlet boundary conditions, and then the PD constraint control problems is to find this mx source term, which is minimize this function j. U is the unknown parameter, unknown temperature, and ud is a desired temperature. So they just want to they just make this unknown temperature similar to this ud with some regularization term for the source term. And the purpose of this control problem is to minimize this j and then find the m, which is the minimize this j. So in this case, for traditional numerical method, they want to minimize, if they want to minimize this one, and they find a new m, and then they have to solve this PD for each different m to minimize this one. But if we can use operator learning, so first phase, we can use operator learning approach to find a mapping from m to u. So we just learn operator from m to u firstly, some with the regularized term or something, and then using this operator network, then we can minimize this j just using this operator from m to u. And then if we minimize this one using gradient descent like something, then for a new m, if we want to find the u, then we just use this network which is pre-trained in phase 1. So this makes faster solving for control problems with sufficiently high accuracy than the traditional numerical method. So it is one of application using operator learning to solve control problem. And lastly, I want to introduce the recent works to solve these complex PDEs. It's also a kinetic equation. When we solve this like complex equation, in this case, the right term has a very complex collision term. Then we can use operator learning to help using pin to solve this equation. So in this picture, if we want to approximate this one, which depends on TV, and the solution is F, and when we use just directly pin, then we can approximate this T V1 V2 as input, and the output is F. But it takes a large time to approximate this one, and also the light term is in loss function. Then we have to calculate this complex collision term to make a residual loss to use pin. So in this work, we want to approximate the operator first using during step 1. So here we want to use from the mapping from F to D, like in this right side. Also, we want to pre-train from the mapping from the F to this F, large F. And we first pre-train these two network during step 1. Then we can use this neural network, this operator, pre-trained operator, during using pin to solve this equation. And then this two pre-trained operator helps this to reduce the computational cost to use pin to solve these complex PDEs. So it is one of our idea to use pin with operator learning. Two approaches, which I explained today presentation. So here is my conclusion. I just briefly explained about these two approaches. First one is PD solver. If we have just one instance of PDE, we can parametrize this solution UTX using neural network, which takes an input TX and the output is U, which depends on TX. And the second approach called operator learning, we can find a mapping from GX to U. For example, if we have a different initial condition GX, and then we can use neural network to learn a mapping from function to function. And then we can use this neural network to find a new for different G or a new G. So today presentation is about these two approaches. So here is my reference. So thank you for attention. Thank you.
Right, thank you, Dr. Lee, for a wonderful talk. Are there any questions from the audience to the speakers? Actually, I have one quick question. So in the last part, when approximating the D and the F operator, as far as I understood, this Poker-Planck-Landau equation and that term involves quite complex term, which involves the multiple integrals.
Yes, right.
So
right.
I wonder, is it, so in your example, do you also carry out some multiple integral part or just one single integral term being involved? I just wonder what exact expression you wish to recover in these two scenarios. Can you comment on that?
I didn't contain what the D and F are exactly how complex, but it contains about the double integral, or I didn't remember exactly, but there are some integrals for these two terms.
Then how you generate the data?
Yeah, so I generate data using numerical quadrature rule. So it takes a lot of time to make a data.
I see.
But when we just pre-train this network, and we can use this network to solve this one,
and performs pretty well.
Yes, because the one trick is to make an input function f, as the professor said. In this case, f is a distribution function.
Right.
So I generate the train data for f using Gaussian, Maxwellian, and its variants.
I see.
So in this case, Gaussian and the sum of two Gaussians or something are used to train this network.
I see. Because the one thing I'm worrying about, concerned about this approach might be that during the pin training, you might have a pin solution at a certain iteration that belongs to the outside of your training input part. Then that might require you to, expect that your operator to extrapolate to a certain extent, unless you will get completely incorrect solutions. So that I wonder, have you encountered such an issue, or your trained network operator is sufficiently good enough that gave a satisfactory return?
I think in this case, the F is not a big difference from Gaussian, because always as time goes infinity, the F goes the Gaussian shape.
Right.
So
that makes
in
sense.
this case, in this case it's easy, but in other case maybe it will be difficult, and it will be very important to how to choose this input function f to help this pin.
Right.
Yes. So in this case, it's more simple.
Actually, I like this idea.
Okay.
All right. Yes.
Can you go back to hyper operator?
Okay.
So I might have missed, but how do you incorporate the result when you said you use that when you for each layer, right?
Mhm.
How do you incorporate the information to when you learn about each? So you said you put inside, but how do you use that and then improve it? I missed that.
Yes. I just lost that explanation in this slide. If we take this input function u and we first discretize this function u, and then the length m vector is in this network, which is fully connected neural network, and this network makes lots of outputs, and each output is the weight and bias in this network. So it is not a new idea. It's called like hyper network, which generates all parameters, weights and biases using this network.
Also, hyper network is something that
Yes. I didn't explain about this one, but hyper network maybe to 20 something.
Nathan Kutz.
Yes. They make this one to use some network to make parameters of other networks, and then this can be help to weight sharing for this network. So the information of this one is shared in this network, so it helps to some task. So
here, then you don't like minimize the loss function or something like that, or it just like loss function is used here, or
yes, yeah. So in this, take this input and they give the output of each layer's parameters, and then I can calculate this from y for each y to g theta uy, and then we just use a loss function, which for this one supervise the loss function for that one. Then in this case, the learnable parameter is only in this one, not only this one.
Okay, so your parameter that you learn is in HyperNet.
Yeah, just in HyperNet. So so they call this weight sharing.
So you might have without using HyperNet, you can just learn the weight and bias, but having HyperNet helps better improving things.
Yes. It's good.
Because that uses you.
Yes.
Okay, thank you very much.
Thank you.
I like this idea as well.
Okay.
Yeah. Okay. After this, the PDEs is based on the input approximation.
Yes, right.
Okay.
Right.
If you use this HyperNet, then you break the input.
Yes, I break this theorem. Yes, right. Exactly.
So okay, you apply that kind of idea and you get the better results. But how do you say about the validity of your method?
I thought it naturally holds because you can make a special case of all the previous layer is independent of U, but the last layer is depending on the U, then actually become a special case.
Okay, so if you forgot the previous steps, then just focus on the last layer, then you satisfy that. Okay.
Yes. I didn't think about that, but his answer is right.
Oh, I thought that is in the paper.
Oh, really?
Never mind.
Okay.
I think you have yes.
And how does it perform in terms of computational cost if you want to and the way and bias each layers?
It's a very good question. When the size of target network is big, larger, then the output dimension of hyper network will be very, very large. But in that case, it has a very big computational cost. But I didn't explain about that. But there are another trick to reduce these output dimensions. If we use the one more input function in this hyper network, which makes the partition of parameters in each layer. So if we use one more learnable parameters in this input function, it calls chunked hypernet, which makes one more input function to choose some which part of network parameters want to give using this network, then the output dimension will be reduced using that idea. Then that idea also works with sufficient accuracy to approximate this target function. So maybe you can find the chunk hypernet, which is in other paper, which variants of hypernetwork to reduce these output dimensions of this hypernet.
All right, for the interest of time, let's thank the speaker at this moment for the wonderful talk. And we're going to have next week's seminar, right? But the next week's ACM seminar will be on the Zoom, and he's from the University of Top today. I hope you can join us for the Zoom next week. All right, thank you very much.